there's a very good perspective for the years to come. So I'll try to give you an overview of all of this today, quickly. So first, I will very quickly say what gravitational waves are, just in case some of you is connected, but there's no idea what a gravitational wave is. It won't know after my slide, but it's at least it's easier to talk about them. I will mention the early attempts of the observations, and then I will spend most of my time talking about ground-based interferometers, which are the instruments that we are using nowadays to detect gravitational waves. Then I will update you on the situation right now, and spend a few words about what's coming in the next next few years, and maybe also in the next decade. Let's see where we can get. So a very quick introduction to gravitational waves. Gravitational waves are they were predicted by Einstein in 1916, just 1 year after he published this paper on general relativity. These are perturbation of space-time, which travel at the speed of light. You can obtain them, you can see them by linearizing general relativity, which means assuming that the perturbation over a flat background, a Minkowski background, is actually a very small perturbation. So you expand everything to linear order, and you obtain a very simple wave equation. So far from the source, there can be a solution which is a wave equation that propagates out at the speed of light. What are these waves? What does it mean to be a perturbation of the metric? So these are transverse waves. They act on a plane transverse to the direction of propagation. They have described a two independent polarization, and you can see their effect on the upper right here. Let me switch the, no, sorry, that's not what I wanted to do. Where is the two? This one, yes, there's a pointer. So you can see their effect would be that of distorting an ideal ring of free-falling particles according to a very precise pattern. Here, time goes left to right. The direction of propagation of the wave is orthogonal to the plane of the screen. And you see that the two polarizations are actually just the same pattern rotated 45 degrees, one with respect to the other. Their effect in this distortion would be a relative distortion of the distance between particles. So the bigger the ring, the ideal ring, the larger the displacement of each particle for its rest position. It's a delta L over L effect. So that's what they do. How do you generate them? Well, you need distribution of masses. Well, nominally, you need a system with a non-zero second derivative of the mass quadrupole moment, which means you need a mass distribution which is not symmetric, it's not spherically symmetric, and is accelerated. Okay, and this will produce gravitational waves. The essential feature here, since we are talking about detection, is the fact that their effect is a relative effect, is a delta L over L, and it's expected for astronomical sources to be of the order of 10 to the minus 21. Now, this is, of course, all of you know what 10 to the minus 21 means, but in terms of, in mathematical terms, but if you stop and think for a second what it is in terms of scales, this means that if we are measuring the distance between Earth and the Sun, we need to be able to discriminate if that distance changes by the size of an atom, okay? Which is a quite challenging measurement. And we don't measure the distance between Earth and the Sun. We measure kilometer scale instruments. So that's a tough measurement to make. Sources for gravitational waves cover a wide frequency band. They go from high frequency like spinning neutron stars or supernova explosion, although we don't know the details of how that happened really. Binary systems that undergo coalescence, which is actually what we are detecting nowadays. And then moving lower into frequency, there are binaries that are stable. There are extreme mass ratio spirals, which are basically what you can consider small test particles moving in the curved space-time created by a much more massive object, like supermassive black holes. And the binaries go all the way to supermassive black hole binaries, which has the same feature of the, as the stellar size binaries, but obviously the dynamic works at much lower frequencies. These things are like 10 to the 8, 10 to the 9 solar masses, and then all the way cosmic strings and relic radiation, so very, very low frequency. And for each one of these frequencies, there's a different instrument that has been either built or proposed. I will mainly talk about ground interferometers. I will also touch very briefly on space detectors and pulsar timing today. So what was the road to get to detection? You know that nowadays we detect gravitational waves. That's a fairly recent thing. But to get there, it took, first of all, it took about 40 years of silence. After Einstein proposed gravitational waves, actually worked out gravitational waves, no one even attempted to detect them. And this was mostly because of two reasons. One, because really people were not sure that gravitational waves were a thing. I mean, there was still big doubts about the fact that they could actually be just an artifact of how you describe general relativity. But if you were to choose the right system of coordinates, the effect of gravitational waves will go away. And if it were to go away in one system of coordinates, then it wasn't physical. Now, that didn't turn out to be the case, and people eventually proved that, yeah, gravitational waves are real physical effects. And but yet people didn't have many ideas of how to detect them until in 1959, Joseph Weber proposed to build resonant mass detectors. So what these are big mechanical oscillators. And what you do, you wait for a gravitational wave to excite them, to distort them with the frequency which is close or at the resonant frequency. And the resonant behavior will amplify the effect and make this resonator ring for a longer time, which will allow you to extract this signal from the detector, even if it's very, very faint. Now, from the initial room temperature in air bars of Weber, through the years, several of them were built. We went all the way to extremely sophisticated in vacuum, cryogenic bars, very, very high quality factor. Some of them, here is a picture of the Riga detector that was operative in Padua until the 2010s. I don't know the exact year it was switched off. In these detectors, it was possible to basically count the single quanta of energy of the ground state of these 3 tons aluminum bar. So it was a quite remarkable object and a quite remarkable detector, except that for their own characteristics, they weren't really well suited for detecting gravitational waves. They were only sensitive at high frequency, the resonant frequency in the kilohertz range. The bandwidth around that frequency was not very large, was about 100 hertz. For Auriga, there was one of the ones that had the larger bandwidth. And the absolute sensitivity also wasn't, now we know because we have much more sensitive instruments and we don't see signals there. So also the absolute sensitivity wasn't good enough. So what these detectors did, they set some upper limits, but they weren't really the way forward to be able to detect gravitational waves. What was instead the way forward? Well, was that of interferometers. The idea of interferometers was proposed by Weber himself at the beginning, but it wasn't until 1972 that Rai Weiss, that is one of the 3 people that shared the Nobel Prize for the detection of gravitational waves, together with Kip Thorne and Barry Barish, worked out a calculation of all the possible noise effect in an interferometer and showed that, yes, an interferometer could be sensitive enough to detect gravitational waves. I didn't mention that Einstein himself, when he worked out gravitational waves, thought they were inconsequential for physics because too small to be detected. But fortunately, he was wrong, at least for these. So Ray Weiss showed that it could be done, and then there was, of course, years of prototyping and applying for funding. But out of these, 2 big projects emerged. There were the LIGO detectors in US and the VIRGO detector in Italy, built by Italy and France, plus some other detectors around the world. But these are the 2 that currently are making detection. So why is an interferometer a good instrument to detect gravitational waves? Here in this illustrative cartoon, you see the effect of a gravitational wave on a ring of particles as the gravitational wave is propagating orthogonal to the screen. And you see that it's really a differential effect between 2 axes, and an interferometer is inherently differential. What an interferometer measures is not the distance, the size of any of these 2 arms between the beam splitter, which is this mirror, this semi-transparent mirror in between, and these two end mirrors, but it measures the difference between the two through interference. So they are inherently differential, which is good. They're broadband, not completely broadband, but a lot more broadband than bar detectors, and they can be relatively easily, not easily, but relatively easily scaled to large distances. So it can be made kilometer scale, while obviously you can't make a resonant bar kilometer scale. They can actually even be made gigameter scale in space, and that's what LISA will be. So, so that it seems like the right instruments, and in fact they are. Now, of course, a modern gravitational wave detector is not a simple Michelson interferometer. It's not even as simple as I will depict it here, but you will see it's already more complicated than that. It's big, it's kilometer scale. It has additional optics and additional cavities to prepare the laser, so to stabilize it in frequency and in spatial profile. The arms, most notably, the arms of the Michelson interferometers are not simple arms, but they're resonant cavities. They're optical cavities in which the light gets trapped for a while. Now, working out exactly how this helps, it's difficult to do in a conference presentation, but if you want an intuitive idea, there are at least a couple of things that you can say. So, for example, you can think that once the photon enters in this cavity, it keeps bouncing between these two mirrors for a number of times on average before escaping. This is effectively similar to making a much longer interferometer, right? So the photon flies for a much longer distance than just the physical distance between these two mirrors. In the real interferometers, this entrance mirror is close to the beam splitter, and this one is at the far end, kilometers away from the beam splitter. Another argument that you can say is that, well, each one of your photons is basically sampling the position of these mirrors. So if you can trap more photons in the cavity, you're basically making more precise measurements, because you can average over the measurement that each one of these photons gives you. So by having more power inside the cavities gives you a better measurements. In fact, this argument of increasing the power is also used for another reason. So as you can see here, I dashed the line that goes towards the detector because we like to keep our interferometers in a condition in which you have almost destructive interference coming out of this part of the interferometer, because it's easier to see small fluctuation on a small signal rather than on a big one. So because of conservation of energy, where is all the light going? It's going back towards the laser, and that's kind of a waste. So what we do is that we put another mirror there, which sends the light back into the interferometer, increasing the effective amount of power which is circulating in these cavities. We call this the power recycling mirror that creates the power recycling cavity that increases the light seen at the input of the arm cavities. And so you can go for like from 10 watts of laser to 10 kilowatts circulating inside the cavities, which is a quite huge number. And so you see that a real interferometer is already quite a bit more complicated than a simple Michelson interferometer. Three of them, three big ones, were built as initial detectors around the world, two in US and one in Italy, Virgo, as I mentioned. There was also GEO 600 built in Germany. It's smaller, and it's not well positioned to contribute to detections, but it has been an amazing test bench, and it has pioneered most of the technologies that are used right nowadays in the bigger detectors. So one thing that you might ask is, why build 3 or even 4? I mean, why not spend all of our money and all our expertise in selecting the best place on the planet and build the super fancy radiation wave detectors? Well, there are several reasons, but the main one is the one highlighted in orange here: coincidence. These extracting radiation wave signals are extremely faint, and extracting them from the noise is difficult, and confusing them with local noise is extremely easy. So one of the most powerful tools that we have to say that a signal that we see in our detector is indeed a gravitational wave is if we see the same signal or very similar in 3 detectors that are spaced out around the globe, but see at the same time the same thing. And of course, it's not at the same time, because gravitational waves travel at the speed of light, which means it's tens of milliseconds to go from Hanford to Livingston to Virgo. So we can account for some delay. And indeed, that delay will help us localizing the source, because gravitational wave detectors are not telescopes. You can't point them. They're more like microphones. But if you can account for the delay that with which each one of them detects a given signal, then you can triangulate and figure out where the detector is coming. This not only the timing, but also the fact that each detector has it doesn't have a completely homogeneous sensitivity to waves coming from any direction and every polarization. It has a so-called antenna pattern. And so by comparing the time of arrivals and the relative amplitudes, you can infer the position of the source. Sometimes better, sometimes not that good. So this is the main reason to have a network of detectors. And then, of course, if you have more detectors, you know, one of them can go offline and you're still able to make detections. You have more coverage because these blind spots of the antenna pattern are not all the same. So the direction in which one is not sensing the other one is. So there are other advantages to this. So those initial detectors went through what we call commissioning, which is something that I guess every high precision physics experiment goes through. These are instruments that don't come with an instruction manual, right? I mean, you think about them, you design them, you build them, and they don't work as advertised at all. You can see here, these plots are sensitivity plots. Without going into the details, these show there's frequency on the horizontal axis, and this curve shows the level of noise in the detector as a function of frequency. The lower it is, the better it is, because it means that the detector is more sensitive. So you see that all of these detectors started from far from their design sensitivity. You have LIGO on the left and VIRGO on the right, just as an example. But then over the years, people learned to use this instrument, understood what needed to be tuned, and in the end, both of them got quite close to the design sensitivity. This was probably the most important thing that the initial detector did. They did set some upper limits on gravitational waves. They didn't make any detection. But the most important things that they did is that they showed that we knew how to design and operate these instruments. Our community knew how to do that. We had a good handle of the objects, and they paved the political and financial, which is very important, way for building the advanced version of these detectors. Now, what are the advanced version? The advanced version of these detectors were supposed to be built, I've been built in the same infrastructure, so same vacuum tubes, same facilities, just replacing the hardware that constitutes the instrument. And the global target was that of increasing the broadband sensitivity by a factor 10. Now, one thing that is important to realize when you think about gravitational waves is that contrary to electromagnetic radiation, in which we detect intensity, and so it's something that goes down as 1 over r square, right? Because it's proportional to the square of the field. Here we detect, for gravitational waves, we detect amplitude. Detecting amplitude means that the amplitude of the gravitational waves goes down like 1 over r, which means that if I increase by a factor 10 the sensitivity of my detector, I increase by a factor 10 the distance at which I can detect a given source, which means that I increase by a factor 1,000 the volume that I'm sampling. So I'm increasing by a factor 1,000 the expected number of events that I can see. Here on the right, you see a cartoon showing the initial detector range, the initial VIRGO range, and the design advanced VIRGO range, factor 10 more. Just to give you, for the one of you that might not realize, I mean, the white dots that you see here are galaxies, not stars, right? I mean, you see the scale on the bottom right here. This little white line is 1,000 times the size of the Milky Way. So each one of these clouds is a supercluster of galaxies. So we can include a huge amount of galaxies and systems in our sample volume with the advanced detectors, which is good. And in fact, it worked. So how are advanced detectors different from the original one? Well, they have a few more complications. They have a higher laser, first of all, which brings the power in the arms to be about 1 megawatt, which is a huge number. They have one additional cavity at the output because we changed the way we read out the signal. So that adds complexity. And they also have another cavity which plays a similar role to the power cycling, except that instead of sending back into the interferometer the power coming from the laser, it sends back into the interferometer the sidebands, the fluctuations created by the gravitational wave for the purpose of amplifying, resonantly amplifying them and then extracting them. So we made them a little bit more complicated. And then we improved a number of other things. We improved suspensions, both the seismic isolation itself, but also the way the mirrors are held, because holding them by steel wires, as in the initial detectors, introduced too much noise in the form of thermal noise. Just the vibration of these steel wires, due to the fact that they are not at zero temperature, and so their molecules and atoms vibrates, are too big for us. So we create monolithic fused silica fibers that can be welded directly to the mirrors. The mirrors are bigger and heavier, which makes them less sensitive to external forces, but also allows us to use bigger laser beams. Then again, by using a larger laser beam, then you can average over a larger area of the mirror surface, and you can average out thermal noise in the form of surface vibration due to the fact that you have some thermodynamics going on there. You're not at zero temperature. Okay, here you can, if you're curious, you can read a little bit more about the improvements, but the main point here is that we ended up with detectors. They are mainly limited by two things. The purple line on both of them here is quantum noise, so shot noise and quantum radiation pressure. And this red line that crosses right in the middle of the band for both of them is thermal noise, mirror thermal noise, which is one of the biggest obstacles in increasing the sensitivity of these detectors. And then there are a number of sources that pile up at low frequency, which is what eventually, we can do something about that, but is what eventually sets a lower limit for what you can do on Earth. You can hope to go much lower than 10 hertz, maybe a few hertz, but not lower than that, because there are huge noise sources at low frequency that prevent you from doing that. And then you have to go to space. So we built these advanced detectors, and here we go. We got gravitational waves. So this is a slide, just a little bit of context. This is a slide that I presented in December 2014 in a conference. And there I was still talking about the timeline of observation. The detectors were not online. And I said, oh, 1 year from now, around 15th of September, we could be already listening to the universe, waiting for a gravitational wave event. Well, we didn't have to wait much, because on September 14, 2015, so exactly when we thought we would start observation, we did start observation, and immediately we saw our first gravitational wave signal. I have to admit it was a lucky first, because we switched on the detectors and we immediately saw one. And it didn't turn out that the rate was 1 per day. So we were lucky to see immediately one. We were lucky that it was a very clear one, high signal to noise ratio, better than anything else we saw in that observing run. So as a first detection, since you want to be quite sure about your claim, as a first detection, you want to have a nice, strong detection. And we did. Nature was kind to us. Although it took months to us to convince ourselves that we were really seeing gravitational waves. And, we spent months convincing ourselves that not only it wasn't a glitch of our instruments, but that no one could have implanted intentionally that signal just to boost the field of gravitational wave detectors. That was a little bit paranoid, but that's what we did. It was also lucky, because it wasn't just, okay, we have seen gravitational waves from something we expected, just we hadn't seen it before. It was lucky because it was from an unexpected source. 2 black holes, 30 solar mass in size, that people didn't even know existed, had no idea how many were out there. So just seeing the first gravitational wave and already attaching a huge astrophysical meaning to it, because there was a trove of information coming out, that was really important and really exciting. This detection was done just by the LIGO detectors. VIRGO was not online yet. There were this was what we call the observing run 01. It lasted for 3 months. There was another one that was called 02 that lasted for 8 months. At the end of both of them, VIRGO was able to join just the last month of 02 because it was late on the schedule. I mean, there are different countries, different schedules, but it joined. And the 01 and 02 runs together, total 11 confirmed gravitational wave detections, about 1 per month. 10 were binary black holes. One was a binary neutron star. These are now published. There are individual papers for many of these detections, but globally they are published on the Gravitational Wave Transient Catalog 1, which you can find easily online, and it's also available at this website that also has data that you can download if you want to play with what this signal look like. So I encourage you to go head on to this website and play with the data if you want. So a few words of what that means. So first of all, here you can see the blue dots are the black holes that were detected through gravitational wave, and the purple one are the ones that were inferred through electromagnetic observation. You see that gravitational waves filled a region of parameter space that was completely empty before. So we discovered a whole new population. It's also true that every discovery here, every detection, basically is a discovery of three black holes, the two that merged and the result of the merger. So every time we got a signal, we add three black holes to this scheme. And so we expect this to grow very fast in the future. Here you also see the neutron star. So a couple of notable detections. GW, so this is the way we label detection. GW170814 means gravitational wave 2017, August 14. That was the first binary black hole detection done by 3 detectors at the same time. Okay, and these are 2 important implications. First of all, the sky localization could be done much better, because to do triangulation you need 3 detectors, not 2. You can do some with 2, but you really need 3 to do full triangulation. And the other important thing is, so as I mentioned, gravitational waves have 2 polarizations. And each detector is sensitive in a different way to the different polarization, depending on its antenna pattern. So in principle, if you have 2 detectors, you have a system of 2 equations for the 2 polarizations, and you can say something about the polarization of the incoming signal. You don't only see the projection on the detector. You see 2 different projections, and so you can say something about the polarization. Now the problem is that the LIGO detectors were intentionally built to be aligned, and basically the same antenna pattern. That was done just to increase confidence in the first detection. But this also meant that they couldn't say much about polarization until you add the third detector, VIRGO, for example, with a completely different antenna pattern. That's the case for VIRGO, in fact. And with this detection, we were already, for the first time, we were able to say something about polarization. And although the signal-to-noise ratio was not very high, because VIRGO is less sensitive than Hanford and Livingston, as you can see here in the upper right, we were able to conclude that models that consider the GR polarization were a lot more favored than models coming from alternative theory of gravity that would assume that gravitational waves can have different polarization form. So that was an interesting result. But maybe the most astonishing detection done during the 01-02 period was GW170817. This was the binary neutron star event. Already from the characteristics, so the frequency and frequency evolution that you see here in a frequency time plot of the system pointed not at the binary black hole system, but the binary neutron star system. But then when we realized that more or less at the same time, there was a short gamma ray that reached Earth, we were all but sure that it was a neutron star system. That was later confirmed. It was interesting, the role of VIRGO in this, because VIRGO did not detect this signal. But in fact, that was very important, because it should have, given the sensitivity, it should have detected the signal. The fact that it didn't detect the signal, it was just due to the fact that the signal, could only be explained with the fact that the signal was coming from one of its blind spots in terms of antenna pattern. But if it was coming from a blind spot, then we had a very important information for localization. And in fact, adding VIRGO, the VIRGO information, the localization of this source was very precise, and it didn't take much to our electromagnetic partner that we sent alert to. We say, oh, we think there's a gravitational wave coming from the direction, to actually identify a transient source in the sky, associate a galaxy with it, and then from there, one of the most complete and amazing observation campaign of an astronomical object started, because it started in gravitational waves, gamma rays, and then all the electromagnetic spectrum down to radio waves for months. And what this turned out to be was a huge trove of scientific results. It confirmed that binary neutron star mergers are in fact the source of gamma ray bursts, at least some of them, the short gamma ray bursts. It also, by comparing, this is also interesting. I mean, we are doing nuclear physics by using gravitational waves. By observing the features of the evolution of the gravitational wave emission, we can draw conclusion about the deformability of the objects that were in the system. Because, of course, if an object starts to be disrupted, then it will change the evolution of the gravitational wave signal. So by looking at how the gravitational wave signal evolved, we could put some constraints on how compact these objects were, so neutron stars. And so we could put some weak for now, but we hope we could do better in the future, limit on the models for the neutron star equation of state, which predict different deformability of the neutron stars. We could also do an independent measurement of the Hubble constant, which was mainly only a proof of principle, because, so you might know that there is a little bit of tension nowadays between different measurements of the Hubble constant. Our measurement fell right in between, and with an error bar big enough to be compatible with both of the other measurements. But it's a proof of principle, because this is, for the first time, a measurement of the Hubble constant done with a completely different instrument, and not relying on the cosmic ladder. This is just, you measure the distance with gravitational waves, and then you compare with the redshift of the host galaxies. And so you have redshift and distance, and you can compute the Hubble constant. Another important thing that we did, which is very straightforward, but had a huge impact on in some sense, is that forget about the 1.7 seconds of delay. We don't know exactly when the electromagnetic gamma ray burst left the system, because of the system might have been opaque at the beginning. We don't know exactly, or it can be the result of the shock wave. But the point is, even if you allows for hundreds of seconds of delay at the emission, these two signals, the gravitational wave and short gamma ray burst, traveled for about 100 million years before reaching us. And the fact that they arrived within seconds, one from the other, means that the speed of gravitational waves has to be really, really close to the speed of light, to the point of 1 part in 10 to the minus 15 or something like that, which rules out immediately, with a single measurement, some alternative theory of gravity, which would predict the gravitational waves have a speed of propagation which is different from the speed of light. It was also, I mean, this is more on the astronomical side that I'm not too strong in, but the electromagnetic observation was actually proof that this was in fact a phenomenon that had been theorized to be a phenomenon that can create heavy elements in the universe, the kilonova emission, and the spectra that were collected in the days and weeks following the event confirmed that this was it. There were found traces of elements that we don't know how else they can be created in the universe. So really, the scientific impact of this event was huge. So in addition to these specific events, of course, we can use gravitational waves. We have been using gravitational waves to test general relativity. We have published companion papers to single detections and to the catalog, in which we compare the signal that we recorded in our detectors using different techniques and different tests. We compare the signals to what we expect from general relativity. Let me skip this in the interest of time. I don't want to go into the details, but all the tests we did to compare the coherence of the signal that we received with what we expect of general relativity didn't point to any deviation from general relativity. Not as exciting as finding a deviation, but anyway, this is what we are finding right now. I mean, these are all tests at the percent level. They're not very precise because we don't have huge signal to noise ratio, but it's interesting. Of course, the other thing that we can do now that we start to collect a number of these events, and not just one. It's not just, oh, I've made a detection. Now we have 10 We hope to have a lot more in the future. We have a little more than 10. It's that we can start draw conclusion on population. How many black holes are out there? How are they distributed? How are the masses distributed in time? These mergers, how they are a function of redshift. So all these things. So these relatively few events are already informing models that before now we're living on very, very little data, right? So even these relatively few events are precious because they're much better than nothing. And we expect to have a lot more coming in the near future. In fact, what I presented up to now was just for 01 and 02. And after 02, there was a suspension of a few months, about 6 months. And on April 1st, 2019, we started the 03, which stands for Observing Round 3, which was divided in two parts with a brief commissioning interval in between to try to fine-tune the instruments. Now, a disclaimer, what you see on this plot, which is an official plot, but it's the number of candidate events. So the number of events that we saw at the first analysis in our data, and we immediately transmitted to the community, to the wider community, to try to do EM follow-up, so to try to find the source. But these are not confirmed events. But even though we expected a good fraction of these, maybe the majority of them, to be confirmed as events, and you can see that the number is skyrocketing. We have like 70 candidate events by now, by the end of 03. So this is coming. I mean, these are becoming very quickly full-fledged observatories producing data at a high rate, and this is really amazing. Right now, we have an average rate of alerts, not necessarily detection, but alerts that is 1 per week. Here you can see when Virgo joined. Now, don't be fooled. The increase in slope here is not because of Virgo. I mean, Virgo is very precious, but it doesn't really contribute in the number of events that we detect substantially. It was a little bit of a by chance that we had this increase as a tail of 02, and then in 03 we expected it. There is an interval here, and then here we have different detectors with a better sensitivity because some upgrades and fine-tuning was done. So it's not the merit of Virgo, although Virgo is playing an important role. 2 events have been published so far and so confirmed for 03. They are peculiar for both because of their masses. So in the GW190425, this is what we think is another binary neutron star merger. We didn't find a counterpart, but we are not even 100% sure they are binary neutron star. They could be black holes, but binary neutron star is the most straightforward. And the peculiarity of this system is that each one of its components has a mass that is maybe a little heavy, but not really out of statistics. But both of them in the same system make a system with a total mass, which, as you can see here, is definitely out of statistics. The black dashed line is the distribution of masses that you have in the known galactic binaries. And on the right here, you see two probability distribution based on assumption that you make on the spin, which, you know, it's a little degenerate with the mass when you reconstruct the parameters. But you see that both of them are peaked on a total mass, which is much higher than what you would expect. This is already, you know, again, it's a new information. We didn't know systems like this existed out there. How does it play with the models of formation and population? This is all something that will come out. This has been published very recently. The other system that is interesting from the point of view of masses is this binary black hole system, GW190412, that were very close together. This is interesting not because the masses themselves, but because it's a system of binary black holes in which the two masses are very different. There's a factor 0.25, 0.3 between one mass and the other, which is uncommon. In all the others, the ratio of the two masses is very close to 1. And in this system, because of this asymmetry, we were also able to detect higher harmonics in the emission of gravitational waves, and not just a fundamental one, which in a symmetric system basically is so big compared to the others that it swamps completely the signal. So yeah, by now we have a system of a network of advanced detectors There's a new one that came online in 2020. It's the Kagura Japanese detector, which is underground and cryogenic. So it has it's testing some new technology. And we are also expecting one in India around 2025. This would be a copy of the LIGO detectors just built in India rather than in US for some clever historical and political reason. So this is how our plan was until very little time ago. So we were going to end O3, stop operation for quite a long time, 1.5 years, and then resume with much higher sensitivities. Now, what happened is that not all collisions are welcome, and we ended up colliding with the coronavirus, like everyone else on the planet. So that changed a little bit our plans, and we don't know exactly how this is going to evolve in the short term. We'll see. We are remodulating our plans right now. As you might imagine, it's not easy to understand what the impact will be in the short term and in the medium term, because even funding with a looming economic crisis and so on, we don't know what's going to happen. But what's going to happen farther down in the future is that so what we want to do when we can finally work on our detector and upgrade them is that, for example, for advanced Virgo, we will go towards its final implementation which is Advanced Virgo Plus, which will be done in 2 phases. One, including that signal recycling mirror, which is not there yet, and increasing the frequency of the laser, the power of the laser, and implementing a technique for reducing quantum noise broadband, which is called frequency-dependent squeezing. This will basically, we expect this, and also implementing Newtonian noise cancellation. Newtonian noise is the fluctuation of the local gravity field because of seismic motion of the rock, but not because of the vibration themselves that get to your mirror, but the fact that the density of the rock is changing, and so it's changing your local gravity field. Then after this, there will be another phase that we will implement for the next observing run, in which we will implement even bigger mirrors and larger beams, and hopefully better coatings with lower thermal noise. And all in all, we should get around the end of the 2020s with 200 megaparsec of range. Virgo is going to be, LIGO is going to be do something similar, but their detector will be a little bit more performing and probably get to the 300 megaparsec by 05, by this 5th observing run. And what next? Well, if you look at this very illustrative graphic, this tries to summarize how old a facility is and what are its limits in terms of how much you can upgrade it. And you see that most of these are on the orange to red line. So we need to think about new instruments. Now, for LIGO, there is maybe space for an intermediate upgrade, which means a new instrument still built in the same facilities, in the same vacuum tubes. Not sure if they will do that. But then after that, that's it also for them. For Virgo, there's no space to improve even further the detector. It's too difficult. The facility, the constraints given the facility are too big. So what we're thinking about is the next generation of gravitational wave detectors. And these are what we call 3G, 3rd generation. The most mature concept is the Einstein telescope in Europe. That will be a triangular 10-kilometer size infrastructure underground. 10 kilometer means 10 kilometer arm length. And being triangular, it can host 3 instruments, let's say 3 interferometers, which a vertex in each one of the vertex of the triangle. But actually, each one of them will be composed of 2 interferometers, one optimized for low frequency, one optimized for high frequency. So it will be a really game changer, step up in the ability to detect gravitational waves. It has been, studies started in back in 2008. A possible optimistic timeline is here at the bottom of the slide, and you see that even with this optimistic timeline, we are not looking at these instruments coming online until the mid-2030s. So it's time to move now if we want to give continuity to gravitational wave detection panorama. Otherwise, we'll be stuck with the current facility being obsolete and not having anything ready to pick up the piece. There's a similar concept that was developed in US much more recently, so it's not clear if it can be developed on the same time scale of Einstein telescope. Americans can be fast and they have a lot of money, so maybe they can they can pick up the slack, maybe not. But you see, it's again a similar concept. The key point here is increasing again the sensitivity and pushing a little bit the low frequency end. What can we expect from these detectors? Well, we can expect to see all possible systems basically that was out there, because their reach will extend to redshift of 100, well before the first stars formed. So they will see all the binary systems that are out there. They will do very high signal-to-noise ratio observation. For most systems, I mean, now we're talking about signal-to-noise ratio of our detector, which is of the order 10 to 20. Here we're talking about hundreds or thousands even, depending on the redshift and the masses. So it's a really game changer. And then these signals, if we manage to extend the low frequency end, they will not last fraction of a second or a few seconds at most in our detector. They will last minutes or even days. So this will be a completely different way of doing gravitational wave science. So here in a slide, there's what the panorama could look like. Now, I had a couple more slides on LISA and pulsar timer array, but in the interest of time, I skipped them. I'm on the video, so you can stop the recording and look at them if you want. This is the panorama that we might expect in the 2030s. So ground-based detectors improve their sensitivity by a factor 10 and move to much lower frequencies. LISA, a spaceborne detector, will be online, observing a trove of sources. There are so many out there in the milliards region, more or less, and maybe pulsar timing array, which is another technique to detect very low frequency gravitational waves, will start to do some. It's already operational, but it hasn't detected anything yet. But their sensitivity goes down with time in a quite regular way. So they're digging deeper and deeper, and maybe something will come out. So yes, I'll keep reading my conclusions again in the interest of time, and I thank you for listening. Hello?
Oh yeah.
Okay.
Sorry, I just unmute myself. Let's unmute ourselves and give Giacomo applause. Thanks for his nice speech. We still have a couple of minutes for questions. And oh yes. Daniel, please go ahead.
Hi, I have 2.5 questions. The half is a quite short one. I remember there were 3 locations proposed for the Einstein telescope, but I don't know which one was chosen. So what will be the location of the Einstein telescope if it's built?
Which one will be the location, we don't know, but right now there are 2 that are, if you want, competing. Now, of course, until it's approved, even as a instrument and study, we won't select the site, but the 2 most likely sites now are one in Sardinia in Italy, which yeah, well, I mean, let me not comment, but that one that has very good geological characteristics, and it's in a not very densely populated area, which from the point of view of noise, it's good. It's also not that easy to build infrastructures there because there are not many. The other one is it's right at the border between Belgium, Germany, and Netherlands. These are the 2 sites that are being considered right now and being studied. And you can imagine a project like Einstein Telescope requires not only, unfortunately, I mean, you wouldn't think so, but it's not only just a matter of which one is the best scientific place to put that in terms of noise, in terms of what you can do, but it's also a matter of infrastructure, of social impact, of economic impact, who's going to pay. So yeah, there are a lot of things that enters into the evaluation of site. Of course, a big part is the scientific part, but the technical scientific part, but not all of it.
Mm-hmm. So when you increase the sensitivity, you can measure further and further, and then you will be able to increase also the measures on the gravitational constant that you could deduct, or the Hubble rate. So there are some theories which states that it's actually not a constant, so it changes over time, at least for different redshifts. And do you think that you could, for example, measure this as not averaging over and give some large error, but rather say that for different z's you measure different values of the Hubble rate?
I would need to think a little bit. I don't want to give you an answer for sure, but of course, yes, you will be, by being able to observe all these different redshifts, you should be able to do the kind of measurement that you have in mind. I'm thinking if there is some fundamental degeneracy that prevents you from actually. But I think if you get to high enough signal to noise ratio, then yes, you should be able to do that, because you should be able to really locate the distance very well. And so yes, if there is some variation with redshift, you should be able to detect that. But I'm not 100% sure about this.
And the last one is that we know that, I mean, at least we suspect that we are living in a four-dimensional space-time, and the gravitational waves are also dissipating as they should in a four-dimensional space. But if there are some extra dimensions, then the amplitude should change accordingly. So can you limit, or can you deduct some limits for these extra dimensions, if there are any?
Well, not right now, not that I'm aware. And again, this is really at the margin of my competence, so I don't want to say something wrong. We will have to understand. So the problem here is understanding if these effects are degenerate with other. So you will never be able to observe the source for what it is really, right? So what you need to understand if the effects that you want to highlight can be explained in terms of other things. I mean, can it be observed as just a systematic error in the distances, for example? And I'm not sure about this. So honestly, I'm not the right person to ask it. I don't want to say something wrong about this. But it is true that gravitational. So it's a little bit of a generic statement, but it is true that a gravitational wave signal by itself carries with it a lot of self-consistency information, at least if you assume general relativity to be right, because the frequency and frequency evolution and phase evolution, especially if you can also measure the higher order harmonics, can give you a lot of information on the system, which then helps you disentangle effects that can be otherwise degenerate. But I don't know about the specific question you're asking.
Okay, thank you.
All right. Any other questions? Oh yeah, Yifang, go ahead.
Hi. Thank you very much for the nice talk. Yeah, my question is, in previous slides you mentioned that so there is an indicator with green and red color, and you say that LIGO, there is still space for LIGO to further upgrade, but for VIRGO it seems to reach the end. So could you say a few more words about it? Yeah, exactly this. So
yeah, well, it's
for LIGO to
it's
upgrade?
mainly really it's a trivial matter of space. Okay. The LIGO vacuum system and the LIGO VIRGO infrastructure, which basically means the room they have, the building they have around their vacuum system, are both big enough that you can add. So, for example, what the next foreseeable upgrade, which is not just an incremental upgrade to the current detectors, but a new instrument, which is not fully 3G yet, will be going cryogenic. To go cryogenic, you need to insert cryostats and the new suspension able to isolate not just from vibration, but you need thermal shields, and these require space. And in VIRGO we don't have it. We will have to redo the vacuum system, but that means redo the facility. So we could as well move to 3G. Now in LIGO they have bigger vacuum systems and bigger buildings around the vacuum system, so that they want to have the chamber they can. For example, in Virgo, we wouldn't have the space for a cryostat outside of the. We would need to build another building for the cryostat, and in LIGO they have these huge halls that host the vertex. So it's a pure issue of space and hard things like the vacuum system and the buildings for the point of view of the limits. Well, and then this is at least what sets the difference between LIGO and Virgo. Then there is a common thing, as you see, none of them for the limits is really on the green part. I mean, Kagra is the only one because this is the only one that is underground. All the others are above ground. So for example, Newtonian noise. Now, I didn't spend much word on Newtonian noise, but one thing that might look amazing, and just let me say it, is that so when a seismic wave, but not the seismic wave of an earthquake, the normal seismic wave, background seismic wave that always exists and always are shaking our ground comes, it can come in the form of a lobe waves, which is something that makes the surface oscillate this way. Now, this displaces the surface of the Earth by a fraction of a micron, but our instruments are sensitive enough that as the waves passes by, there will be a moment in which the sound is a little higher on, let's say, the back of the testmass and a little lower on the front of the back of the testmass. And so there will be more gravitational attraction from the back. And then as the wave travels, the crest of the wave will be in front of the testmass and the gravitational attraction will be reversed. And these are the type of phenomena we are fighting against. So when you are underground, there's a little less of these because the compressibility of ground is less than just replacing air with ground as your wave goes up and down on the surface. So underground facilities, from this point of view, have less limits. On-ground facilities have the same limits. So in Virgo, you also add the limitation of space, and you go on this red area here.
I see. Thank you very much.
We will take the last question, then we'll have a coffee break. Please go ahead, Kai. Kai? Kai, can you hear me?
Yeah,
go ahead.
Can you hear me now?
Okay. Yeah. We take the last question.
Yeah, so this is Kai Schmitz. Thank you very much for this nice talk. I think on your second to last slide, or one of the few last slides, you showed this nice overview of how we can probe gravitational waves across a vast range of frequencies, including the pulsar timing arrays and space-based interferometers and so on. So my question basically is, there's this one gap around frequencies of 10 to the minus 6 hertz, where we don't really have any observational strategy. And then it also stops at 10 to the 4 hertz, right? So it's hard to go to very high frequencies. So I'm wondering whether you are aware of any, maybe also very futuristic concepts or ideas how we could probe gravitational waves in these two frequency ranges.
So you're talking about this gap right here.
Yeah, exactly.
No, indeed, I don't. I mean, there's some things that I didn't put on this plot, which are mission concept, space mission concept mainly, that aim at filling the gap here, because as you can see here, there's also a gap. And this is a very interesting gap, not as much as for the fact that it has sources that you wouldn't see anywhere in other, also, but one of the very interesting reasons to cover this gap is that actually there is a very realistic prospect of observing sources in the LISA band. And then over the years, over not hundreds of thousands of years, but over few to 10 years, follow their evolution down to the ground-based detector range where they will coalesce. This was the case, for example, it was calculated that if LISA were in space, I think 10 years ago, more or less, then it would have detected the system that ended up being the first detection of LIGO in the frequency. So 10 years ago, LISA could have said, oh, look, there's a binary black hole system that is going to coalesce in your band in 10 years from now, and probably give us the day and the time exactly. So there are a trove of proposals to cover these. Right now, I'm not aware of much going on in this frequency range here. It's also maybe not deemed as interesting as this one. But yeah, honestly, I don't remember hearing about many proposals in this frequency range here.
Okay, yeah, thank you very much.
You're welcome.
Okay, let's unmute ourselves. Thank you, Giacomo, again. Our host.